Greetings and salutations, magical chemists. This is a great point in the unit to go ahead and recap all the ways that equilibrium is connected to the units that have come before. There is, of course, the connection between Gibbs free energy and the equilibrium constant, or as we like to call it, negative rattling. This equation is provided on your equation sheet. How delightful, your formula chart. So, the thing that people tend to forget about this equation is the negative. Also, for the R value, you're using the universal gas constant, but you want the energy R. Because, of course, this is Gibbs free energy. So you need the one with joules in it. And then, of course, your temperature will be in Kelvin. Be careful, K doesn't stand for Kelvin. That's your equilibrium constant, which your formula chart will tell you if you ask. Remember that this can be rewritten to solve for K, which is not on your formula chart and is something totally useful to know. All right, and then if we go further back in time, you might remember electrochemistry. Well, if you calculate the cell potential, E0, you can also use that to calculate Gibbs free energy using the negative nth calculation. And then, of course, once you know Gibbs free energy, you can work backwards to find K. Okay. Now, negative nth, of course, has a negative sign. It also uses N, which is the number of moles of electrons being transferred. So you have to look on the charge of your ions and how they change. Your oxidation states, woo, that's totally a thing. And of course, Faraday's constant, which is constantly the same thing, and it is given to you on your formula chart. All right, I know you know these things already, so let's go ahead and try some practice problems and make sure we remember how to do them. In our very first practice problem, we would like to find Gibbs free energy. Of course we do. Now, we are given an equilibrium constant of 5,000 at a specific temperature. So, I would like you to take a moment, pause the video, and try this on your own, because you can. Make squiggly lines too, because it's fun. When you're ready to check your answer, unpause the video. First, because you want the Gibbs free energy and you're given the equilibrium constant K, we need negative rattling. So then we're just plugging in the values that we know. When you plug in your values, don't forget to convert to Kelvin. Other than that, this is just straight up plug into your calculator and get a delicious number. Now your calculator will give you negative 22,023 joules per mole reaction. But you may remember that delta G tends to more naturally go into calculations into units of kilojoules per mole, just because, one, we need to worry about sig figs, and two, that's a giant number. So you don't have to, but you can rewrite this as negative 22.0 kilojoules per mole reaction. Notice we had to keep 3 sig figs, so even if you didn't convert to kilojoules, you still would have had to round to 3 sig figs, which would have meant scientific notation, so lots of reasons to use kilojoules. All right, let's look at the second problem. Yummy, yummy electrochem. All right, you'll notice that we are given 2 half reactions, and we are going to making a voltaic cell. Yum. Do you remember what it means to be a voltaic cell? I hope so, because it's totally on your semester final. Well, a voltaic cell is something that is thermodynamically favorable, which means it's going to have a positive cell potential. You need that to figure out what's going to be what's being oxidized and what's being reduced in your cell. Once we figure that out, so we're going to use that to calculate the cell potential and the free energy change and the equilibrium constant. So many fun things. So remember, the equilibrium constant is K. The free energy change, that's Gibbs free energy, so that's our delta G they're asking for. And then, of course, cell potential is E0 cell. So I strongly encourage you to go ahead and pause the video and try this on your own by making lots of squiggly lines. Actually, I lie. You should try it by doing chemistry. It'll be great. And then whenever you are ready to check your answer or you need a hint, go ahead and unpause the video. All right, try it. Okay, before we can calculate any of these things, well, I guess we have to start with the first one. We have to calculate the cell potential. So we are given 2 half reactions, and the goal is, first, with these half reactions, hopefully you recognize that these are both reduction half reactions. How did I know that, you ask? Well, I noticed that the electrons are reactants. They are being added. Also, of course, if you notice the change in oxidation states, both of these are starting with a +2 oxidation state, and they're both ending with an oxidation state of 0. So in that case, they are being reduced. Their oxidation state is literally becoming smaller. Remember that one of them we're going to keep as a reduction half reaction, and the other one is going to be flipped to make our oxidation half reaction. And then when we add them together, the goal is we will get a positive number. Well, you can probably tell just by looking which number we have to flip to be able to add them together and get a positive number. It's the number that's more negative. And that makes sense. The number that's less negative, our very first reduction potential, well, it has a higher reduction potential, so it's the one that's going to be reduced in a spontaneous reaction. That means that we already know the reduction potential for our voltaic cell. It's going to be the negative 0.45 volts, because this is the one that's going to be reduced as written. To get the oxidation half reaction, we just have to flip this one. And excuse me, I meant the oxidation potential. Of course, if we wanted the half reaction for oxidation, we would have to flip the reaction. But we don't actually need that. We just need the values here. All right, so now that we have our two potentials, reduction and oxidation, we just add them together to get the cell potential. Okay, so that's when we add them together, we get 1.92 volts. Notice a positive value since this is a voltaic cell. All right. If you haven't tried the rest of this because you're like, electrochem, what's electrochem? Well, now we've walked through the electrochem, so if you haven't tried them yourself, you should totally try those other two calculations. And then when you're ready to check the answer, go ahead and unpause the video. Okay, hopefully you realized before you can calculate the equilibrium constant, you need to calculate delta G. And since we have the cell potential, that means we can use negative nth. Now, to use negative nth, you do have to find N, which is the moles of electrons being transferred, but that's actually pretty straightforward here. We don't actually have the final balanced reaction, and you could write and balance it if you want to, but you don't have to, because we have the two half reactions. And notice, in each of those half reactions, well, 2 electrons are being gained by the species being reduced, and since this, of course, will be flipped around, for the oxidation, there are 2 electrons that are being produced by the species being oxidized. So that means in this reaction, there are 2 electrons being transferred. Well, I should say 2 moles of electrons, because we are talking about a mole of reaction, of course. Then we just need to plug in our other values. Now, it is totally to your advantage to plug in the units when you're doing a problem like this, because it allows you to help remind you what the units should be. Although, to be fair, I hope you know the units for delta G by now. So let's go ahead and get our answer. So the answer we calculate is in joules per mole reaction. You may be going, wait a second, I don't remember there being joules in those units. You lied to me. Well, I didn't really lie. You just have to remember that a volt is technically defined to be a joule per coulomb. And the coulomb will cancel out from that, leaving us with our joules. And then, of course, moles of electrons cancel out, and it's always joules per mole reaction because that's how we define it. All right, now that, of course, is not rounded for sig figs, and we want pretty numbers. So let's go ahead and get a lovely, pretty answer for delta G with the correct number of sig figs and kilojoules per mole reaction because that just makes more sense. So that would be negative 371 kilojoules per mole reaction, which is just a more reasonable number. However, I didn't want to get rid of that joules per mole reaction because we need that, because we still need to go back and solve for K, our equilibrium constant. So let's go ahead and look at our negative rat link. Oh, rats. So of course that's the equation for negative rat link, but we have delta G and we're trying to find K. So let's rearrange this a little bit to make our lives just a little less confusing. Well, if we rearrange this to get the natural log of K on one side, that means the natural log of K is going to be delta G divided by negative RT. I think it's a little less messy. I've started doing it this way instead of taking everything to the power of e, just because then everything's an exponent and super squished. So this way, let's go ahead and solve for the natural log of K first, and then we can plug back in and solve for K. All right, so let's plug in the numbers we got. Now, when you're plugging in for your value of R, hopefully you wrote the units, because it might remind you that you need the delta G in joules when you're plugging into this equation. Unfortunately, because this isn't a separate part A, part B, part C, we have to use the full value that we calculated for delta G. Yum, no sig fig rounding. But once we plug those in, we are going to get a rather longish number in our calculator. So notice that the negatives are going to cancel, so we'll get a positive value here. So my 149.54, that's equal to the natural log of K. So that means solving for K, we need to raise both sides to e to the power of. which is kind of a ginormous number. Hopefully your calculator can handle it. So finally we can do sig fig rounding. Notice we keep our 3 sig figs, 8.82 times 10 to the 64th. That k totally greater than 1 by a lot. You would expect that. Remember, a voltaic cell. So this is at least a way you could check your answer, because if it's a voltaic cell, not only should you know it will have a positive cell potential, it will have a negative delta G and a k greater than 1 because it is thermodynamically favorable. All right, so hopefully that was fun and exciting. Let's try one more practice problem, and then we'll be good. You'll notice this is a multi-part problem. It turns out these kitchen sink problems are very commonly going to be part of your free response. So what better way to practice than in an actual free response? So once again, I am going to strongly encourage you to draw squiggles on things. No, just kidding. To try these on your own. And then when you are ready to check the answers, go ahead and unpause the video. All right, now that you've totally tried the problem, let's check answers. If you said positive value of entropy, you would be correct. Now for the reasoning, it is enough to say, well, there was 1 mole of a gas, of your gaseous reactants, but that produced 2 moles of gaseous products. Remember, increasing the amount of gas is the best possible way, or the easiest and the quickest, to increase your entropy. For part B, you may be wondering how you're supposed to figure out what happens to delta G if you don't know the value for delta H. Well, they may not have told you if this was an endothermic or exothermic reaction, but they gave you enough information to figure it out. Notice they said it is observed that greater amounts of PCl3 and Cl2, aka your products, are produced as the temperature is increased. Well, if your reaction shifts to form products, when you increase temperature, that means heat is acting as a reactant, which makes this an endothermic process. So let's look at the equation for delta G that contains delta H and delta S. More specifically, delta G is equal to delta H minus T delta S. Remember, this is totally given to you on your formula chart. Well, you may recall that if you have a positive, or delta H, an endothermic reaction with a positive increase in entropy, this is in fact only going to be spontaneous at higher temperatures. That's because to be spontaneous, or thermodynamically favorable, well, we want to have a negative delta G. And the trick is, we need this term to be bigger than delta H because the whole thing, T times delta S, is negative. So the increase in temperature as this term gets bigger, that means we're becoming more and more thermodynamically favorable as the temperature increases. So now we just need to explain that using our words. And the idea is, because delta S is positive, increasing temperature will increase that negative T delta S term. So delta G will become less positive and eventually more negative, either way more thermodynamically favorable, as the temperature goes up. And there you have it. I think the math is more straightforward than the words, but you know, gotta be able to explain things. So let's move on to part C. For part C, they say they're gonna throw some helium in there. Now that sounds like fun, whee! But actually, hopefully you remember that helium is of course a noble gas, which means it is an inert gas. So they have added an inert gas. So hopefully you recognize this is kind of a trick. There's not going to be any change in the partial pressure of the chlorine gas, because adding an inert gas that doesn't participate in the reaction won't affect the position of equilibrium. So once you recognize that helium was an inert gas, this question was fairly straightforward. So that leads us to the very last part, part D. So we are decreasing the volume. What will happen to the number of moles of chlorine gas? Well, remember that decreasing the volume means you're increasing the pressure, which means the reaction to reestablish equilibrium is going to shift towards the side with fewer moles of gas. In this case, that's going to be the reactants. By shifting to the side with fewer moles of gas, that's going to decrease the pressure and reestablish equilibrium. Well, remember, this question asked about chlorine, and chlorine is a product. Since we're going to shift to favor reactants, that means the moles of chlorine are going to decrease. And there you have it, kitchen sink equilibrium. It's like we threw all of equilibrium together. But wait, there's more. In fact, we still haven't talked about an entirely different type of equilibrium problem, solubility equilibrium. So whenever you're ready to learn about the glories of that fun subject, go ahead and move on to the next video. Thank you for playing. I'll see you there.